Good afternoon, everyone. What I'm going to cover today is overwriting the global offset table exploit. And we will overwrite the global offset table with our shell code. So when a print function is called, it won't call print, it will call our shell. So we're going to have lots of fun. Let me just jump right into our terminal where we belong, where we live. And here's where the magic happens. So just let me open up the folder here, and I'm going to show you my first demo here is just a simple printf, hey, like a hello world, but my way. And with this printf function, a lot of people just don't really think about what's happening when a printf function is called. And you sort of need to know that because we end up using procedure linkage tables, global offset tables every time a function is called. So what I'll do to try to explain this is I made a fancy dancy diagram here. I am not an artist. I will never be an artist. Let me just load this up. If it would. Is my virtual machine locked up? I think it is. Click on it again. Usually that'll make it work. Okay, so here we go. So what we have here is our basic C program, just a printf with hello world. So what happens is when that printf function is called, it goes to the procedure linkage table. And the procedure linkage table just has a whole bunch of jumps to the global offset table. So it'll know where to jump to get our printf address. Now the global offset table gets the puts address. Now where this is just a simple string, it's going to go grab puts instead of the printf, and it'll go to the library, grab it, and it will store the address for the function of printf. So what a procedure linkage table is a table in the executable binary that helps dynamically link and resolve functions at runtime, especially for shared libraries. Okay, so how it works: on the first call to the function, the PLT redirects the call to the resolver in a dynamic linker loader. Sounds confusing? It's really not. The resolver finds the actual location of the function and updates the GOT. So GOT gets updated. Now, when the function goes to call at a future time, it doesn't have to go through that because it's already loaded in the global offset table. So what we're going to do is we're going to be bad girls and boys here, and we're going to put a system function in on this and take it over. But what I want to do before I jump into the actual exploit, I'm just going to run this program through GDB just so you guys can see what's happening when a printf function really is called. So gdb/q, I have it called hey. Let's have a look. Disassemble our main function. And as you can see here, there's a call to printf right here. I'm going to put a copy and put a breakpoint in here. And I will just run the program. Okay, so then we're down to the print. And as you can see, it's saying printf at a procedure linkage table already right here in the assembly code. What happens is if we wx and have a look, or actually let's do 3 strings or 3. Okay, so when we come and look at this call, so this call function is going to the PLT. And as you can see right here on the PLT, as I said, there's jumps. So this jump is jumping to this address right here, which will be on the global offset table. So let's take a look. And if we XWX this one and have a quick look, you can see right here, all of a sudden it's at the global offset table. So that's what happens when printf gets called. It goes to the procedure linkage table, and then it gets called to the global offset table. So if we have an exploitable binary where RELRO is only partially enabled, and I will show you in just a sec, we will quit out of this program. RELRO is partially enabled for this one right here. So what happens is we can overwrite the global offset table. So I'm just going to change to my root account here. That's where I have um, my PETA plugin, and I showed people how to install the PETA plugin last time or the time before. So I'm going to open up my next program, and I'll give you a look at this program too before we do. Okay, so this one here I ended up not using, so just ignore that for right now. I got to take that out for class tomorrow. But here we have the function string copy. So it's going to copy argument 1, which is our first input, into this pointer, okay, on the stack. Now the second string copy, it's going to take the second argument and put that onto the pointer. So this is where we overwrite the global offset table. So now when this printf gets called with printing sh, for shell, what's going to happen? It's going to call a system function with sh and give us shell control. This one isn't that difficult, so I'm going to take you through it. And if you guys have any questions, feel free to hit me up. I'm usually around my computer during the daytimes anyway. So what we'll do, we'll open up our GDB /q RELRO, and of course we disassemble the main function. And let me open this window up so we can see everything. Okay, so as you can see, stack cookies are there. Whoops, gone a little too far here. I can't control this thing at all today. Okay, so we're going to look for our 2 stir copies. And as you can see, there's one right here at this place. So let's put in a couple breakpoints here. So we'll break at this place and then come down to our second stir copy. And let's copy that one and put a breakpoint in on that. So that's about all I need to do right off the get-go here. So it's going to run with 2 one-word 4-byte inputs, and that was right by the stir copy, the number 4. This will be on my GitHub too if you want to try it out on your own. So what we'll do, we'll run the program with 4 A's and 4 B's. So that's argument 1 and argument 2. Okay, so it's to the first breakpoint, but I don't have my display set up yet. So what I'm going to do, I'm going to show you a very fun, cool way that I just learned actually to find the stack size perfectly for every single 32-bit system. And here is what it is. And as you can see, 18. So now we can just hit this display, if I can spell right, hit 18 words hex from the ESP. So now we have our beautiful display. Okay, so let's start finding everything on our display as we go here, just for a learning experience. And as you can see, EBP is F0C8, so 378. So this is our EBP. So of course, right next to our EBP is a return function. And we can just copy this and hit XWX and paste this in. As you can see, return to libc start main. So that is our return address. Here's our argument count. So 0 is the first argument, and that's the program name. Second argument is A's. Third argument is B's. So what we'll do, this is the argument vector. So this stores the actual argument. So we can do XWX of this one. And then this pointer here, I'm going to have a look at copy X, examine the strings at this point. Oh, so that's the first one, but we have 3 strings here stored. So let me hit this again. And as you can see, here's our 3 arguments. Okay, so that was the argument count right here. And here's the argument vector. And this is our full stack. This is our full stack. So as you can see, 35C is all A's. So if we look right here, we can see that our A's are already loaded up here, and our 4-byte count is loaded up here. So that's pretty cool. So we found that. Now, with finding our pointer, we found a count, we found this. So where would our pointer be? Well, our pointer, we got to do a little bit of assembly here. And right before the stir copy, right here, you can see load effective address, LEA, load effective address in assembly. And it's loading an effective address at ESP0x18. And this is going to be our pointer that we made. So let's do XWX ESP plus 0x18. And that puts us at 174. So if we go back up here, 174 is right here. And our actual pointer is this one right here. So what we can do, we can copy this and examine it. And as you can see, this points to our address right here. So that's our pointer. So now we know where everything is on our pointer. We're right before the stir copy. So what we're going to see this 174 get overwritten by our first argument, which is the A's, which I showed you was right next to the pointer and right before the bit count. So I'm just going to hit next instruction. And as you can see, it is now overwritten with A's. Okay, so now the second argument, examine the string. The second argument is going to be loaded up right in this. As you can see, the A's are still loaded up. It's overwritten here. If we hit continue to head on down to our next, you can see that the pointer itself is already overwritten. So now what we're going to do in our exploit, we're going to put the print address in this place and get it set up in the global offset table. And then we're going to come in and we're going to put as argument 2, we're going to put the system address, overwrite the global offset table and get a string when it hits that print function we put in. So fun. So there's our arguments there. Now we're at the second breakpoint. I should do display 3 instructions of EIP. Whoops, little I. So as you can see, we're right at the second stern copy here. So everything's already been pushed to the stack. The B's have been pushed to the stack. The 4-byte of the stern copy is right next to it. Here's our pointer is already overwritten. Now what's going to happen? We're going to get a sig fault here because that's not a valid address to overwrite with our A's, right? So if we just hit continue, as you can see here, sig sev. Okay, so it's not going to work. But I just wanted to show you basically where everything was in the stack and what was going to happen. So our 4-1s got overwritten. Our 4-2s tried to overwrite to the A's and it crashed. Okay, so what I'll do, I'll quit and let's get into some fun stuff. So let's get into the actual exploit now. I hope that was a good enough explanation. So let's get right back to it. We got to put our breakpoints in again and copy and paste. And let's get our second stern copy. Excuse me, bit of a flu floating around here. My boyfriend's sick right now, and I'm getting kind of choked up myself. Okay, so 2 breakpoints are set. We already know where everything's going to be on the stack. I just showed you. We just ran through the program. So I won't do all that stuff again. So the first thing is first, we got to get this program ran so I can get the system address. So we'll run the program just with these functions again. So I'm going to print system, open up a new terminal. And just to keep notes here, I keep notes in my terminal. It's just easier. So copy. And let's put our system function address in right here. That's all I need from that right there. Now I can do object dump, use tr, and now I'm going to find the print address. So yeah, as you can see right here in our symbols, we got printf is right here. So here's the function address for printf. So we just copy this. So this is what I'm going to overwrite the initial pointer with. And then we'll overwrite the second pointer. Whoops. Let's get back here and print. Paste that. Okay, so we're just about ready here now. So what we'll do, gdb/q RELRO, and just similar main, and put in our breakpoints again. Copy, paste. That's break 1. Now let's get break 2. And paste that in. Okay, so we have our 2 breakpoints set. So now let's run the program, and we're going to put in argument 1 and argument 2, and we're just going to use Python like we have in the past. So we'll run $Python C print, and we're going to put in our 4 bytes and close this off. And then we put in another $Python/C tick print, and 2, 3, 4, and close it off. Okay, so now let's minimize this window a bit. And so the first address we're going to put in is our print, because we want the global offset table to have the print address, and then we're going to overwrite the pointer that points to that print address with our system, and then we should get shell. So what I'll do first, and then this little Indian convention, so it goes in backwards. So 0C, A0, 04, 08, and let's go 10, 33, E5, and B7. Okay, so now we have our exploit set up. Let's run this. So I'm going to display 18 words in hex from the ESP. I show you a handy dandy way I just learned. Let me get a drink here. Okay, so we know our EBP is right here. Here's our return address. Here's our argument count. Here's our argument vector. Here is our pointer. Here is our first argument. So if I examine the string, or actually examine the hex at this point, the string with the, as you can see, this address has our 0C, which is our print address right here. Okay, so this is our print address, and it's already been loaded on the stack with the 4 byte next to it for the stir copy, and this is the pointer here. It's going to be copied into this address and then overwrite the global offset table with printf. So what I'm going to do is just hit next instruction, and as you can see down here, our variable has been overwritten. If we hit continue, you can see here the pointer itself has been overwritten on the global offset table with the printf. Okay, so what's next? Already loaded onto the stack will be our system address, so XWX. And let's paste this one in. And as you can see, it's B7E53310, which is our system address. Now, same way our system address is going to get written here onto the printf, and then the global offset table is going to point towards system with the printf function. Then when the printf function is called later in the program, it's going to be a system shell. So what we will do, we will hit next instruction and continue. And as you can see, new process 2598 is executing new program bin dash. We got shell. That's the cool part about this. So that is how you overwrite the global offset table to get shell. This is because we have partial RELRO enabled. If we have full RELRO enabled, which you have to do at the GCC, then this wouldn't be able to happen. But these are all exploits you have to know and build up and in your toolbox as an exploit developer. So I hope you had fun. I had a lot of fun showing you guys. And we will be back with return-oriented programming exploits next week. And I can't wait to get into that with you. I'm already having a blast with it. So that's all I have. I hope everyone had a great day, and I shall see you guys soon.